Hello, everyone. Good afternoon on this beautiful day. Uh, so, welcome back. And today we're going to talk about lists. So, but before we start on this new topic, I want to make sure that there are no questions, if there are any questions about the stuff that we have done with the three types of sorts that we have talked about: bubble sort, insertion sort, selection sort, and your upcoming homework, which is due next Thursday. So if you have any questions about any of this stuff, please don't hesitate to raise that question now before we get started with a new topic. You can raise your hand, or if the spirit moves you, just unmute yourself and start talking if you have a question.
Professor, I have a question.
Yes, Eric.
And the part of the driver, right? And we need to use the enum as a loop like you did to pass all of the different values that are in the enum, like for example the array sort,
Mm-hmm.
to create each one, right? Kind of,
Yeah.
like a loop.
Like a loop. What do you mean by a loop? Like in what way are you talking about a loop?
For example, like going through the different sort types. For example, we do a loop to go through the three sort types and run it as many times as we need.
The run sort will tell you which sort you need to run. Okay? If you look at the driver interface for that, let me just bring that up on the screen here so we can see it. Okay. This is the driver interface that we're looking at. Okay. And if you see that there is create array, and it tells you what kind of array it wants and what the size of the array is. Okay, so there's no loop here other than filling up the array itself, right? Run sort tells you what sort it wants you to run. It tells you what kind of an array it wants you to sort. And it tells you what the array size is and how many times you need to run the sort. Okay, so essentially what your run sort would look like, if I could just take a stab at it here with some pseudocode. Okay, let me just take a stab at it with some pseudocode. I'll have to switch screens. Any questions about this, about these particular two methods that are in your driver? There's no other, there's just two methods in your driver that you really need, and your main method, obviously, that you need to write. But if I switch over to the pseudocode of run sort, okay, then it will look something like this. Okay, let me switch over to here. Where is it? Hang on one second. Right here. So run sort would look something like this. Okay. Run sort. Sort type. Array type. Array size. And num times, right? These are the parameters it takes. Okay, so here's where you would have something like a switch statement. Okay, you can say switch, switch on. Actually, let me take that back one step. Okay, for I equals 0, I is less than num I plus plus. Okay, that's how many times I'm going to run the sort. Okay, and the first thing that I need to do to run the sort is I need to get an array. So I would say array is equal to create array, which is a method that we have, right? Create array, array type, and array size. Now you have your array that you want to sort, right? I have an array that I want to sort. Now what I'll do is I'll call the sort that I need to call, right? So this is where I'll switch. Switch on sort type. Case. Bubble sort. Bubble sort. Then you would call bubble sort. Your bubble sort, you would create an instance of your bubble sort, right? So bubble sort, we'll call it BS is equal to new bubble sort. Right? And then you say BS dot sort array. Case, insertion sort. Okay. Are we okay so far? Does that answer your question, Eric?
Yes, yes. Now I see how we're using the enums.
The enums are basically, what is it telling me that it wants to do? Now, the only problem with this particular thing here is the switch statement is inside the for loop. Okay, and I don't want to do that because I don't want to create a bubble sort every single time I go through the loop. So let's redo this so that it works a little bit better. Okay, I'll show you another way to do this. So we're going to start with a switch. And we're going to say sort interface. Interface sort. Okay. It's just a sort interface. It's sort, a variable called sort of type sort interface. Okay. Now I'm going to have a switch on sort type. Okay. Case, bubble sort. That means sort is equal to new bubble sort. Case, insertion sort. Right? Then it's going to be sort is equal to new insertion sort. Okay. And, you know, obviously case, selection sort, blah, 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 same thing. Okay. Sort is equal to new insertion sort, selection sort, sorry. Okay, that's the end of the switch. We have set the sort. Okay, and now we have the for loop. For I equals 0, I is less than num, I plus plus. And here's where you go, array is equal to create array. Array type. Array size. You have to pardon my handwriting. And then you can say sort, that's sort, array. And that's it, that is your for loop. Okay? So somebody might say, okay, you know, how am I creating a class of type sort interface when sort interface is a sort, is just an interface, okay? And like what we're doing over here, what we're doing over here, over here, over here. All of these sorts, the sort, bubble sort, insertion sort, and selection sort, all of them implement the sort interface, Okay, as long as they implement the sort interface, I can put them into a sort variable, which is of type sort interface. Okay, that means even if bubble sort did a whole bunch of other things beyond just sort, I wouldn't be able to access it through sort. I would have to access it through bubble sort. But if I'm just looking to use whatever is the sort interface part of that class, I can look at that class as just a sort interface. I can pass it around as a sort interface, as a matter of fact. Any questions about that? So this would be like a shell of your sort. I mean, obviously there's more detail that I have to go in here, but that's just generally what this should look like.
Professor.
Yeah.
And the array type will be used by Mimir, right? So the array type that is passed, that will Mimir decide, right, what to pass.
Yeah, I will. When you say Mimir, I'm the one who writes the, so I will call your create array, and I will say, create me an array of this particular type and this particular size. And then I will go through it and make sure you created the right kind of array.
Also, it's not necessary for us to create another switch inside specifying the type of array type, like increasing
inside the create array.
No, the runs are like for the different array types.
No, if they call you, if you are called with a particular array type, you're just running the sort on that array type. That's it.
And it will, for example, it will work the same for something increasing as something decreasing.
Right. Because you're calling your create array over here, and you're telling it what kind of array type you want it to create and how big is it.
Oh, so the create array is the one that should know what type of array is.
Right, exactly. So the create array will have a switch statement like this one, right? Let's say, depending on the array type, I'm going to create the array in a certain way, right?
Okay.
Could be a switch statement, could be a bunch of if then else, if then, so on and so forth. You can do it either way.
So final question. I'm done. I'm sorry for asking too much. And I did my bubble sort, such it works for arrays, and I put it in ascending order, I think it was.
Mm-hmm.
So when you pass a decreasing one, it will be the same thing?
If it is ascending order, that means it's already sorted, right? Bubble sort will go through it and say, yep, it's sorted, right? If it's decreasing order, bubble sort will go through the trouble of sorting it and putting it into increasing order, right? So bubble sort is going to work on whatever array you give it, and the final result is the array that you give it will be sorted when that is done.
Okay. Thank
okay.
You,
Good.
Professor,
how come, Eric? How come you're showing up in here twice?
It's because I'm having a problem with my audio in my laptop, so I'm using my cell phone to use the voice.
Ah, okay. I was wondering.
I'm
There's
sorry.
2 of you today. Anybody else? Go ahead.
Yes, Professor. The sort interface sort is that an enum or
the what?
What is that? The first thing that you put on the method.
Sort interface.
Yeah, sort interface. Sort, is that like an object?
It's like a variable. Yeah, I'm defining a variable called sort. It's of type sort interface.
Okay.
And
so
sort interface is something that you are given with the homework. You have that.
Okay, I understand now. Got it.
Okay. You can, yes, you can. Cruz is asking, can you create things that are of interface type? Yes, you can. Okay. Like here, bubble sort, insertion sort, and selection sort are classes. They're not interfaces. They are actual classes, right? So I could do something like this, right? Where I can say bubble sort BS is equal to new bubble sort, right? I could do the same thing for insertion sort, insertion sort. IS is equal to new insertion sort. correct? Selection sort the same way. But when you look at the bubble sort, insertion sort, and selection sort, all of them, like bubble sort, implements sort interface, right? We know that. That's how it's declared. It implements the sort interface. So really, it is a sort interface. It's kind of like inheriting from this class above you, which is called sort interface, but it's not really a class, it's an interface. Okay, so I can do this. I can do sort interface, sort is equal to new bubble sort. Because bubble sort is a sort interface. It implements the sort interface. And so does insertion sort, and so does the selection sort. You can do that. I cannot say new sort interface. Okay, I cannot do that. That is not valid. Because sort interface itself is not a class. So I can't say, give me a new one of sort interface. It's not a class, it's just an interface. So that would not work. But I can take a class that implements the sort interface and put it into a variable called sort. Okay? One more level of detail here. This is helpful programming knowledge. Okay? We look at the sort interface over here. Public interface, sort interface. Okay? And the sort interface has one method in it, public void sort, and then it takes some kind of an array of, I don't know, object. I don't know what it is, but let's say array. That's what the sort interface looks like. Okay? It only has one method in it, sort. Now let's take a look at a class that implements the sort interface. Say public class. Okay? We're going to call it some sort. Implements the sort interface. Okay? So this class, since it implements the sort interface, must have in it a public void sort object array, right? It must have that, not like that. It must be the method, and it has some kind of code in here. Okay? So far, so good? That's what we have to have, because we say we implement the sort interface. But let's say whoever implemented this class added this other method to it. Okay, public void some stuff. System dot out dot println. Hello. That's all that method does. It just says, it's called some stuff, and it prints hello. Okay? So let's create an instance of this some sort that we just created. Okay? So I can create some sort, SS is equal to new some sort. Right? I created a new some sort. I can now do SS dot sort an array, And I can also do SS. What did I call that method? We can call it, it's called some stuff. That's all okay, right? This is fine. I can call this some sort. I can call this, I can call create a class of type some sort, because some sort also has the sort method, which comes with the sort interface, and it has this other method, some stuff. Okay, so I can do both of those. But what happens if I do this? If I do sort interface, si is equal to new some sort. Okay, I should be able to do some sort sort interface, sort interface dot sort, and I pass in some kind of an array. That should be okay, because sort interface has that method si. Okay, but I cannot do si dot some stuff. That is not allowed, because the variable si refers to an object of type sort interface only. And sort interface, as we know from here, only has this one method in it, sort. So if I call a variable of type sort interface, I can only call it to do sort. I cannot call it to do some stuff. If I create the variable as a some sort, then yes, I can access both. Yes, go ahead. Who was asking a question?
Yeah, I was gonna just specify. So you can only use methods that are specified in the interface, basically.
If you are defining the variable as an interface variable, yes.
Okay.
Okay.
Yeah.
The reason why this is the case is because you can create an object. I can create an object. Okay. I can say public class OO implements sort interface, and also it implements the search interface. I can implement multiple interfaces, right? So if I create an object that is sort interface, if I say sort interface si equal new OO, this si can only do sort interface. It cannot do search interface. Okay? I can do si dot sort array. That is okay. I cannot do si dot search array target. I cannot do that, because si in this case is just a sort interface. Even though my object OO implements both the sort interface and the search interface, I can, if I define the variable as a sort interface, I can only call the sort interface part. Is that clear, or is that still confusing? I'm assuming that this is new. Yes, Eric.
That's clear. It's like restricting if you only need that part of the class.
Right. You're saying that I'm looking at this through the little lens that says this is only a sort interface.
So this is useful only when you have different things that use the same sort interface.
Right. This is useful in all kinds of ways. Okay. And you'll find that there'll be uses for it in programming a lot in Java.
Didn't know. Thank you.
Okay. So, all right. So having completed all of this and covered all of that, let's talk a little bit. Any other questions before I go on? I'm eager to jump into the topic that we want to talk about today.
Sorry, I just wanted, Professor, just wanted you
Johnny,
to,
go ahead.
yeah, just to repeat that last part that you just said about what you had on the screen. I didn't, and it wasn't quite clear. So could you just repeat it one more time?
If I create the object OO here, like I just did over here, new OO, and I
Right.
put it into a variable called SI, which is of type sort interface, even though the OO object implements both the sort interface and the search interface, in other words, OO has two methods in it, sort and search, right? It can do both.
Yeah.
But if I put that object into a variable of type sort interface, that object, SI, that variable SI, can only access the sort part because the sort interface only has the sort method.
Okay. All right. That makes sense.
If I put it into a search interface, interface, SSI, we're going to call it, is equal to new OO. I can do SSI.search array target, but I cannot do SSI.sort array because the SSI is a variable of type search interface. And it can only do the search part because that's the only method that's in the search interface. It cannot do the sort because SSI is not an interface that includes sort.
Okay. Yeah, that makes sense.
Okay?
Okay. Appreciate it, Professor.
So that's how you can use a variable containing a real object that is of a type interface. Okay? That's how you can do it. Okay, let's continue over here. So we started talking about lists. Okay? And we said lists have some, set of methods that we want to be able to use because lists are very useful to us. We use them a lot. Okay? And we want to define what a list can do. And we said lists have this kind of objects, these kind of methods associated with them. And we said that once we define the set of methods that define a type, like a data type like this, like a that contains data for us, that holds data for us, we're going to call that an abstract data type. And that abstract data type is that of a list. Okay? And this list can do the following. Any list that you create can do the following. It can add an element. It can add an element at a particular index. It can remove an element from a particular index. It can remove all the elements, empty the list, in other words, replace an element at a particular index, get an element at a particular index, ask, is the list empty? Give me the size of the list, in other words, how many elements are in this list. And we want to be able to do something called add sorted, which means every time you add an element to the list, make sure it puts itself into the place where it is in a sorted order. So if I have a 1 and a 3, and I want to add a 2 in an add sorted manner, the 2 is going to find itself in between the 1 and the 3. Okay? So those are the lists, the topics that we want to deal with, okay, in a list. Now, how do I implement the lists? Well, I have options of how I implement the list, it turns out, because one of the options is to use an array, right? I can use an array that, so this is if I have a list as array. Okay, so I have an array. I'm given element 1, put it in the list, it goes over here. Give it me element 2, it goes there. Give me element 3, it goes there, right? So All right, so I have an array and I can add elements at a particular location. I can add elements to the list, and the list is contained inside my class. It's contained as an array. Okay, so when I implement my list, all of my methods that I just showed you, add and add sorted and added an index and so on and so forth, you will then put the stuff into the array. So if somebody said, add this element, so here we had so far, add E1, add E2, add E3, okay? And now if I say add E4 at index 1, well, what's going to happen is E4 is going to replace E2 at index 1, but I want to move E2 and E3 over. So I'm going to move E3 to here, and I'm going to move E2 to there, and I'm going to put E4 over here, right? Correct? So I know how to do all of this in an array because we created a class called Better Array that can do all of these things for us, right? So I can just make use of that array, Better Array that we created in order to do these operations for me and maintain my list for me in the order in which I want to maintain it. Okay, so that's actually, so one of the methods in here I think is replace, right? Remove, no, replace. There's a replace method. So if I say somewhere in here, I can say replace E5 with whatever is currently at E2, at index 2. So E2 will be taken out and E5 will replace it. Okay? Remove. Okay? So if I say remove element at index 0, okay, what's going to end up happening is this element is going to get removed and all the elements move backwards. E4, E5, and E3. Okay, that's what that results in. Okay, so I can maintain a list inside of an array. Okay, I can maintain a list inside of an array. But as you can see, maintaining a list inside of an array, when you insert something at a particular index, requires taking elements and moving them along, moving them over to make room to put the data where you want to put it. When you want to remove something, you take it out, and then you have to shift everything else over to the left in order to keep everything together at the beginning of the array. All right, it requires moving objects around. There's a lot of copying that happens in here. Copy things over to the right to make room to put something, copy everything to the left because you're deleting something. So doing things as part of an array can actually be time consuming. We want to see how time consuming it is, but so we're going to implement a list. One of your homework assignments is going to be after you finish the sorting, you're going to come up with a list and you're going to implement it as an array. And if you want, you can use Better Array as the array inside your class. All right. Or we're going to learn this other method of also doing lists and data structures. So this abstract data type called the list that we are talking about over here is a data structure. It's called an abstract data type because it defines what this abstract type can do. And now you implement a class that is not abstract, that actually implements all of this functionality that you want. Okay. It's also called a data structure because a data structure is some kind of an object that holds my data in a particular way. Okay, so this is holding my data in a way that actually behaves like a list. We're going to learn other data structures that we want to learn about. Okay, queues and stacks and trees and graphs and hash tables and all other kind of data structures, which are ways in which we take our data and we structure it in a certain way because it turns out to be beneficial for us to be able to manipulate the data in our programs. Okay, so if I have data that I would like to use in my program that behaves as a list, I'm going to put it into an abstract data type called the list and implement that as a list and use it, because that is beneficial to me in the way I'm writing my program. Okay, so this data structure is called the list, or abstract data type list. And this is its implementation if I do it as an array. It turns out that there's another way. Any questions about this? Okay, so this is if I implement it as an array. But what if I wanted to create something, instead of it being put into an array structure like this that has a certain number of entries, places where I can put things at index 3, 4, 5, 6, 7, 8, so on and so forth. I wanted to be able to sort of like say, all right, my first element is E1, my second element is E2, my third element is E3, and my last element is E4. Okay? I don't want to put them into an array. I want to have them kind of like free floating out there. And I want each element needs to know who is the element that comes after them. So E1 will know that E2 comes after him. E2 will know how that E3 comes after him. And E3 will know that E4 comes after him. Okay? I want to know that. Because now, if I want to insert E5 in between so this would be add E1, add E2, add E3, add E4, okay? And now if I'm saying, say, add E5 at index 2, okay? So we can think of these elements, even though they're not in an array with indices, we can think of this as 0, we can think of this as 1, this is 2, and this is 3. So insert E5 at index 2 is going to replace E3 at index 2 and move E3 over, okay? So what we want to do here does not require any moving at all, because all I'm going to need to do is take E3 and create an E5 that comes before it. I can create an E5 that comes before it. I can just create it. And I can tell E2 to now, your next element is no longer E3, your next element is this one. And we tell E5 that his next element is there, which makes essentially this index 2, and this becomes index 3 and 4. I didn't have to move anything. E3 did not have to go somewhere, and E4 did not have to go somewhere. I just had to be able to create this E5 somehow, make E2 know that he's followed by E5, and tell E5 that he's followed by E3. Okay? This is called a linked structure. You can see why it's called a linked structure. Okay, this is not 0, this is 2. Okay, this is called a linked structure. Okay, it's a linked structure because obviously elements are linked to each other. There's one or two other links that we actually need. Okay, one of them is the link that says where the start of the list is. Start of the list, and we make it point here. Okay, or instead of start, we're going to call it the head of the list. Okay, this is the head of the list. And we could also have another one at the end over here, which is the tail. Okay, and you can think of the head and the tail as being the ends by which you grab your linked structure. Okay, and in this case, if you think of it as a chain, the head is in one hand, The tail is in the other hand, and the chain in between is hanging between the head and the tail. Okay? And therefore, the head says, my first element is E1. E1 says his next element is E2. E2 says his next element is E5. E5 has E3 and then E4, and that's the tail. So I'm grabbing my chain, and obviously the more elements I add, the longer the chain becomes in between the head and the tail. Okay? Questions before we continue? How do I create these links? Well, obviously, an element is not going to just be able to just point at the next element, because I don't know what kind of elements I'm putting in here. All of them don't need to know who the next element is. So it's not something that's part of the element. So what we do to create this is we create this notion of a node, okay, like a basket. And this basket's job is going to be to hold elements and to have a pointer to the next node. Okay, so I'm going to create something called a list node. Okay, I'm going to call an object a list node. And the list node is really a basket. And this basket has two containers in it. One for the element, and one points at the next node. So when I put my elements into the list, it's going to be element 1 is here, and the head is pointing at element 1, right? Because that's the first element in my list. And the tail also points at element 1. Correct? And there is no next pointer because there's nobody after me. That's add element 1. What does add element 2 look like? Well, add element 2 will create a new node. Okay? It will put element 2 in it. It will make the first node, the node before it, point at that next node, and it will say that there is no one after it, and it will update where the tail is. Add E3. Well, it'll create a new node. It'll put E3 into that node. It will make this node point at that node to say he's next, and it will update the tail. Right? And now if somebody comes and says add E4 at index 1, well, this is 0, that's 1, that's 2, right? I want to put E4 in the place where E2 is, and I want to move E2 and E3 over, but I don't have to move anything, I just have to change the pointers, okay? I have to create a new, I have to create a new node. I'm going to put E4 in it. Okay. I'm going to change this pointer over here, that one that comes from that node. I'm going to make it point to here. I'm going to add a pointer from here to there. So now he's index 1, he's index 2, and he's index 3, and the tail did not have to change at all in this case because I inserted something in the middle. Notice that when you insert something in the middle, all you got to do is change the pointers around, and now all of a sudden the list is reconfigured. Because if you grab it from the head side and from the tail side, what's going to be hanging in between them is this link chain, necklace, chain, whatever, bracelet, that is formed by all of these nodes being linked together. And all that this involves is manipulating these links and creating the nodes and putting elements in them and then manipulating the links so that we keep it all together. Okay? How is that? Any questions about that? We're going to do an example of that in a programming example we're going to work on right now. But if you have any questions now is a good time to ask that. Okay, no questions. So we're going to do an implementation of a linked list. We're going to work on a linked list together. So I'm seeing a question now for the first time. Zahra is asking a question. So we would implement another class like better array? You could, or you could use better array yourself. You would declare a class that uses better array inside of itself. Okay? We'll talk more about that. Okay, I don't know if you understood my answer, Zahra, but let's talk more about it later. Okay?
Yeah, I understood it. Thank you.
Okay. So, all right. So I'm going to stop sharing this, and I'm going to share my code, my Eclipse with you. So right here. Okay, I hope everybody can see that. So we have defined here for us in this project, this list interface. And let's take a look at the list interface. The list interface does the following methods. It has a size. It tells me how many elements are in my list. It tells me, is it empty? It can take and add an element of type I. I is a generic parameter. We're going to see what it is up here. So list interface, and look at this in here. Okay, it's a little bit more complicated than what we have seen before. What we have seen before is I have a parameter of type I. Okay, that's what we saw in better array, correct? It's just a parameter. When I instantiate this class, I tell it make it for this type, like we did for better array. Okay, but this one contains more information than that. It says it's of type I, and that type I must extend the comparable interface. Whatever object you're going to give me must extend the comparable interface. In other words, it implements the compare to method. That's me telling you, okay, you can tell me, here's the object that I want it for, but whatever object you give me must extend the comparable interface. And if it does not implement the comparable interface, then some super class of it must implement the comparable interface. In other words, I can have a class that implements the comparable interface, and I can inherit from it and inherit from it. And now I can put that object into this list because this object inherits from a class that implements the comparable interface. So it has access to the comparable interface. So this is me saying that whatever object you give me must either itself extend the comparable interface or some superclass of it must implement the comparable interface. And the object, the generic parameter is of type I, is I, the letter I, okay? So I can do add an element of type I, add an element of type I at a particular index, add sorted in element I, we're gonna see how we do that, get an element from the particular index, replace an element at a particular index, remove an element from a particular index, remove all elements, and that's all only methods that we have, okay? So if I want to create a linked list class, it must implement all of this. Okay? It must implement all of this stuff. Okay? So let's make a class that implements that. Okay? Hang on one second. I just need to double check something before I go on and make a fool of myself.
Professor.
Yes.
Quick question. So we're gonna do all ourselves, right? Because I think in Eclipse there is already a class that has all those methods. Array
Which
list.
one?
I think there is something called array list that do all of that.
Yeah.
Or-
Well, we're going to implement, we're not using array lists.
Oh, okay. So we're doing ourselves.
Yeah. Java has everything we're going to do this semester already exists. Okay? Everything we're going to do this semester already exists. Java has a library for lists called ArrayList. Java has something called a queue. Java has something called a stack. They have something called a binary tree. They have something called a hash table or a hash map. They have all of these things already written. And you will use them in your real life when you are a programmer. Okay? But here we are in learning mode where we're trying to learn about these things. And in order to learn them the best way possible, in my opinion, we have to implement them. Okay? And whatever we implement is going to teach us what it is that we are using here. Okay? We're not going to use ArrayList. We're going to use Better Array. I like Better Array. It's not as good as ArrayList. ArrayList is a much more developed class, but Better Array is the one that we have developed, and we're going to use it for this semester.
Okay, Professor. Thank you for the explanation.
Sure. All right. So I want to create a class called linked list. Okay. File, new, class, and I want to call this class linked list, and it implements the list interface. Okay. And linked list also must have this notion that it uses an element I, which extends comparable. Comparable, or some super of I implements comparable. Okay. So that's what the linked list class. And of course, once I've defined how I can be, then I'm implementing the list interface for I, and this I must also, I can't state everything again over here, but it's just enough to just say I here. And the thing that we're missing here are the methods. So let's go to the source, and we're gonna override and implement the methods that are in the list interface, which basically gives us all the methods that we need. Okay, these are the methods that we need in our list. Okay, in our linked list. And now we'll write code to fill all of this stuff up over here. So before we do that, I need to define this structure that we call the node. Okay, we have to define a structure because we need a class that defines that node. Okay, so let's create a class, file, new class, and we're going to call it linked list node. Okay, it's going to be a linked list node. And the linked list node does the same thing. It needs to take the same kind of element that we want to put into our list, right? It needs to be of type I, which extends comparable, or some superclass of I implements comparable. Okay, so that's my class for linked list node. And what's in my class? Okay, well, I obviously in my class I need to have room to put an element of type I, which is the data that I have, okay? And I need to be able to have a pointer to the next element, okay? Which is a pointer to a linked list node of type I. And we're gonna call that next, the next element in the list, okay? So, and when I create a linked list, when I create a node, I have a constructor over here, public, linked list node that takes no parameters in this case. No, it takes some data, okay? Data, and this data is equal to data, right? And this next is equal to null. We want to define it so that there's nobody coming after me. Or if somebody calls me and says, here, public linked list node I data and linked list node next, okay? Linked list node of type I next. Well, then they're giving me both data fields, and I'm going to put them in here. This data is equal to the data, and this next is equal to next. Okay. So what else do I need? I need a bunch of getters and setters. I want to be able to get the data, set the data, get next, and set next, right? But we have methods that we can do that right here, where I can say file. In here, I can say source, generate getters and setters. And I want all the getters and the setters for the data and the linked list. And now I have my getters and setters. Okay. I have get data, get next, and set next. Okay. And that's essentially my node. There's nothing else to the node. Okay. This is my node. Okay. We have defined the node. And now let's go back to our linked list. Okay. So what's in my linked list that we still need over here? We need a whole bunch of code to go in here. But my linked list is going to consist of two things, two nodes, right? Two nodes, one pointer that points at the head and one pointer that points at the tail. I need both of them, right? So this is private, linked list, node of type I. We're going to call that head, and private linked list node of type I, which we're going to call the tail. Okay. And we're going to also have this private element in here, private int size equals 0. Okay. We're good. So far, so good. Anybody else have any questions about this? So let's continue. Okay. Let's create a constructor for this class. Okay. Public linked list. And when we create a new linked list, we want to set this head is equal to null. This tail is equal to null. And this size is equal to 0. There's nothing in the list, it's empty. Okay? Let's do the ones that are the easiest methods to implement now. Okay? So we've implemented the constructor. Let's implement the size method. Well, the size method is very simple. Return this size, right? That's it, we got the size. That's easy, right? How do I do the isEmpty method? How do I do the isEmpty method?
Well, if the size is 0, doesn't mean that it doesn't have anything.
If size equals 0,
Then it's empty.
return true, else return false, right?
Yes.
Correct? There's a shorthand for this. Okay? There's a shorthand for this. And the shorthand for this looks like that. Return size equal, sorry, I like to always say this, that size is equal 0, false, or true. This is the same code. Okay?
So if I wanna like simplify it, I'll do that instead. How does that work? Like,
So this works the following way. This is an if then else statement. Okay? Here's the way it looks. This is the condition that we're looking at. If this is true, question mark, is this true? If it's true, return false. I mean, return true, right? Sorry. Return true, else return false. So this expression over here, return, will check this first. And if that statement is true, it returns true right here. Okay? If this statement is false, then it returns false. It's a shorthand if then else statement.
it's a really handy shortcut.
It is a very handy shortcut. Okay? It is a very handy shortcut. It's a good one to know. And it exists in other languages as well. Okay? So we want to be able to do add and blah, blah, blah. Let's do the easy ones first. I like to do the easy ones first. Remove all. Well, that's easy. We want to make the list empty. How do I make the list empty? I said this dot head is equal to null. This dot tail equal to null. And this dot size is equal to 0. The list is now empty. Okay? What happens to all, if I had a bunch of things in my list, what happens to them? What happens to them? Let's take a look on, let's go back to the whiteboard writing thingy that I do over here. Okay? I'm gonna stop sharing here. I'm gonna bring this back up. Where is it? Right there. Okay, so we're going to share this screen. Okay, so if I have a list, and I have a list and it contains a bunch of things, what happens to those things when I do that? So I have the head is pointing at a node, and this node points at another node, and this points at another node, and this one has no next, but that's also the tail. Okay? This is my list. It has element 1, element 2, element 3 in it. And now I go to my class and I say remove all. So what it's going to do is going to say the head is no longer pointing at this, and the tail is no longer pointing at that, right? Because they're both null now. Correct? And we said the size is equal to 0. The question is, what happens to these nodes in Java? Where do they go? You would agree with me that my linked list is now empty, right? Because the head is null, the tail is null, and the size is 0. So as far as my linked list is concerned, it's an empty list. But my question is, what happens to these nodes? Anybody? This is an interesting question for Java.
Would it still be there?
Okay, they're going to be there. Thank you, Zahra, for that. Thank you for that. They're going to be there for now, but they're no longer part of my list, right? Correct? They're no longer part of my list, but they are somewhere in memory still in my program.
Yeah.
Java has this thing called the garbage collector. Have you ever heard of the garbage collector? It's the sanitation department of Java. Okay? What the garbage collector does is periodically the Java virtual machine that you are running in stops your program. It says, take a break. Okay, have a drink, whatever you need to do, just take a break. The virtual machine takes over. And if you know like how programs work, programs have a stack. And the stack, every time you call a function, okay, it creates a stack frame in the stack, okay? And that's a stack frame for method 1. Okay, method 1 calls method 2, it creates another method 2, okay? And method 2 calls method 3, so on and so forth, okay? There's a bunch of stack frames. And in those stack frames are the variables that are defined in that function. The parameters that it holds, whatever variables, I, J, M, whatever are the variables here, okay? List, something else. Every method has variables that it's playing with, right? When we create a method, we give it some local variables. It has some parameters that it's holding on to that were passed into it. So the garbage collector stops, and in another part of memory, there is something called the heap. And the heap is down here in the memory. This is my heap. And if my program created objects, any object, whenever you say new array, new anything, the array is allocated in the heap. If I say new linked list, the new linked list gets allocated in the heap. So here's my linked lists. So this list thing here points at that linked list. Okay? That linked list itself points at a bunch of nodes, right? The linked list points at the first node with E1. It points at the next node with E2. And it points at the next node with E3. All of those are in the heap. Okay? And the linked list points at the last node saying that is my, so I'm going to make this a little bit bigger so that we can see it. So my heap looks like this. There's the list. That list points at element 1, which then points at element 2, which then points at element 3. That's the nodes, right? And the list also points at E3 because this is the head and that's the tail. Okay, and there's a pointer coming from lists pointing at this list. So what the garbage collector does is it goes through the stack, finds every variable in the stack that has a pointer to an object in the stack, in the heap, and says, okay, this object is owned. Somebody points at it. And it says, and it traverses from this object to anything that it goes through step by step. And it says, oh, okay, this object is owned, this object is owned, this object is owned, everything is owned here, nothing changes. All right? If I go to my list now, and I change it, I say remove all, what is that going to do? If I change it, what I'm doing is I'm getting rid of this head pointer and I'm getting rid of this tail pointer, right? That's what I did when I made the remove all. That makes these three things that are linked together, nobody is pointing at them from anywhere. So when the garbage collector comes and looks at list, it says, okay, list is owned, okay? And it goes through everything else that is in your program, and everything else that is owned will get a check mark, and everything that is not owned, in other words, nobody is pointing at it, are considered no longer used. And what the garbage collector will do is will then erase these things out of the heap, freeing up the memory. Okay? That's how objects that are no longer being used are taken out of memory, is by the garbage collector. So it comes and looks at the list and it says the list is there, so that's owned. I'm not going to collect it. It's not trash. I'm going to leave it here. And it goes through all the other objects in your heap, and there'll be a whole bunch of them. And all of them that end up receiving a check mark because some stack frame points at that object, and anything that that object is linked to is also traversed. So the garbage collector follows the links and marks everything that it passes through as owned. And if it is owned, it stays. If at the end of going through all of the variables and traversing all the links, there are still some objects in the heap that are not owned, the garbage collector says, that is garbage. I'm going to throw it away, free up the memory. Okay? I assume that this is all new information, but that's how Java does it. Other languages do it slightly differently, but this is how Java does it, because Java runs in a virtual machine that is actually executing this compiled code that you created in Java, executing this P code, it's called, in a virtual machine, okay? And that virtual machine is the one that does all of this garbage collection for you. Any questions on garbage collection? So you got to take out, I'm confused. Why we made a pointer in the linked list node and then two more in this class? Okay, could you explain that question to me, Gracia, again? Because I'm not understanding your question.
Yeah, sure. So when we were writing it out, we made a like a linked list node called next in one of the classes, and then we did a head and a tail. So I'm just confused why we did both of those.
Okay, so I need to know where. Well, here's I can do a linked list with just a head. Okay, I can do a linked list with just a head, but check out what happens if I don't have a tail. Well, I'm going to answer your question, but one step at a time. So head. Here's the head. There's nothing in my list. It's null. I get a new element. I create a node for it. I put it in here. I make it the head of my list. It doesn't point at anything afterwards. I want to add another element. Well, I got to go to the head and I got to follow the list until the end, create a new node, put element 2 in it, link this node to that one, and then put element 2 over there. Okay, I want to add element 3. Well, I got to come to the head and I got to travel the whole list, starting element 1, element 2. Oh, I reached the end of the list. Okay, create a new node, put element 3 in it, and link this node to it. Okay, so every time I want to add something to the end, I got to find out where the end is. I don't know where the end is. This list could have 700 elements in it. In order to find the end of the list, I got to start at the beginning and follow the chain one at a time until I get to the end. Oh, this is the end. I got to put it here. Okay, so I can create a list with just a head, but it's much easier if I also maintain the tail, because now I know where the end of the list is always. So when I want to put something at the end of the list, I don't have to follow the list from the beginning until I find the end. I know exactly where the end is at. Okay, so that's why I'm keeping a head and a tail, in order so that I can always find the tail, the end of the list, easily. Okay, in our linked list, if there's no more questions on this, I can switch back to the code to answer Grecia's question. In my linked list over here, where is it? Right there. Share that screen. Okay. In my linked list, I maintain a reference to the head and a reference to the tail. That's because I want to always know where my end of my list is at. I always want to know that. Okay. And that's why I have two of them in here in my list. This is my linked list class. Okay. In my linked list node class, a node consists of only two things. Every basket or node that contains my data, my elements, contains the element, and then a pointer to whoever comes next. So my node knows the data that it holds, and it knows also who comes next. But my list knows who my first node is, that's my head, and it knows who my last node is, that's my tail. Does that answer your question, Grecia?
Yeah, that makes more sense. Thank you.
Okay, sure. All right, so let's continue. So we want to be able, we did the easy ones. We did the size, the is empty, okay? And we did the remove all. So far, everything is cool. We're gonna do, let's do one or two of these methods over here. Let's do add. Okay, and here's where I need you guys' help in making this add. How do I add something to my list? Anybody?
You can just, with the index, you can get the name of the linked list and, apply that element or assign that element to the index at that array. Or
It's not an array, it's a linked list, right,
in the
Johnny? It's an array, it's a list, it's a linked list.
Yeah.
So Eric is suggesting that we can use the tail reference, right? We want to find where the tail is and we want to add it to the tail. Correct? So we want to look at the pointers to put it at the end of the list because that's what add does. We want to put it at the end of the list. Okay, so I could do something like this, right? I could say, I would create a new node, like linked list node of type I. Node is equal to new linked list node of type I, and it's going to contain the element that I want. Okay. I'm going to put the element in there. So now I have a node that contains the element. And what Eric is suggesting is I can just say, I want to connect it to the node that is the one that is at the tail. So I can say tail dot set next to be this new node is the tail, is the new, make that whatever is the current tail, give it a next pointer to be this node. And I can just say this dot tail this dot tail is equal to the new node that I just did, right? Correct? And then I can say this dot size plus plus because now the list contains one more element in it, right? This dot tail dot set next. Why is this giving me an error? No, we didn't. Oh, we never saved it over here. Maybe that's why. Okay, so we hadn't saved it in the other file. All right. So anybody see any problem with this code?
There's no head. Like the
Huh?
head. Do
Yeah,
we need the head?
We're
as
not
well?
using the head at all, right? So that's one. That's a good point. That's a good point. We're not doing the head at all. We're just worried about the tail here. What else is a problem here? That's a good one. What else is a problem here?
Size,
Huh?
the size maybe.
Yeah, well, we're doing the size. What's the problem with the size? We're just increasing the size of the list by 1.
Oh, okay. Oh, yeah, I see it. Okay, never mind.
What else? That's not a problem, the size. What else is a problem? Could be a problem. So we're not doing anything with the head here. Yeah?
I was gonna say, like, for the this tail equals node, does it have to be dot equals or something like
No.
that?
Dot set, no. No, this dot tail equals node, that's correct. Otherwise, the compiler will be yelling at us here. What if my tail is null? What if my list is empty? What happens here? If my list is empty, what's going to happen here? The program is going to die right here. When it's running, it's going to die at that statement right here. Why will it die?
Because there's nothing in the like list.
Right, because the tail itself is null, right? I'm trying to say what some null object set its next pointer to be this. You can't set a pointer on a null object, right? That's called a null pointer exception. Your program will die. A horrible death. Okay? Because we're not taking into account that first case, which is adding the first element into my list. In other words, I start out with an empty list, and now once the list is no longer empty, I want to add elements in this manner. So let's do that. Let's take into account whether the list is empty. If this dot is empty, if the list is empty, what do I want to do? Well, I want to make that one node that I have, the new node that I have, I want to make it both the head and the tail. This dot head is equal to the node, and this dot tail is also equal to the node. Right? Else, the list is not empty, which means I'm going to go grab the tail and I'm going to add the thing to it. Add the tail, and in both cases, I'm going to increase the list, my size of my list by 1. So if the list is empty, that's good. That's not a problem. I have a new node. That new node is both the head and the tail. It's the first one and the last one. I'm going to set them both to be that node. Otherwise, if the list is not empty, meaning I do have a tail, okay? Oh, there's another one that's Eric is checking here. Do we need to check if the element itself is a null? That's a good question. All right, but first let's finish this. This code over here looks like it will work just fine. If this list is empty, then make it the first and only element in the list by making it the head and the tail. And if the list is not empty, that's okay. We know we have a tail. Let's go grab that tail, make the node to be its successor, the next, okay? And update where the tail is at now. And that code is a very legitimate add method for our linked list, okay? What else do we have? So any questions about this? About this method, the add method? Okay, so we have a bunch of other methods that we want to add here, but none of them are going to be doable in the amount of time that we have today. So what I'm going to do now is we're going to stop. I'm going to take attendance, take any questions that you might have, and then we'll finish this on Monday when we get together. Okay? So,
Professor,
yes.
you didn't say what happened when the element is null. Will it work anyway?
So if the element is null, I don't think that we have anything in our behavior that is saying, don't put a null element into my list. Okay? It'll be interesting to add that to the list interface over here. Because if I look at the list interface, the documentation for the list interface, add, okay? A reference to the element to be added to the list. All elements being added to the list must implement the comparable, blah, blah, blah. Returns true if the element was successfully added at the given, this is the given index. The reference to the element to be added to the end of the list, all elements being added to the list must implement, blah, 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 Java comparable. All right, so there's nothing in here that says you can't give me something of type null. Okay, but if we wanted to protect against that, then one thing that we could do over here, before we even start, okay, before we even start, if we can say if element not equal to a null, then you want to do all of those things. Otherwise, we don't do anything, right? Otherwise, we don't do anything. If the element is null, then don't do anything. Just go. Just return. We didn't add anything to the list. That's how we would handle that if we wanted to in here.
Okay, thank you, Professor.
Okay? So, but since we're not doing that, I'm going to just remove that code from here. Okay? All right, let's stop sharing this. Take attendance. I'm going to stop the